leaves, fluorescence, absorptions, emission, reflectance can be useful for this kind of spectrometers. And also we have these laser scanners, and then liquefiers, and then cryocoolers, cryostat, uh, and these hyperspectral imaging cameras from Spekim, along with a multispectral imaging solution as well. Then we have other products also which might not be relevant for these conferences. Uh, Starting with this, since this conference is all about the nanomaterials and defined kind of applications based on materials, so we have this system from old age, who is having their cryostats and cryocoolers built for different kind of customizations, different kind of 4 Kelvin, 10 Kelvin or 6 Kelvin measurements. Whoever wanted to use a low temperature applications, have any materials, some kind of samples, and wanted to create an environment of the sample by putting the sample into the cryostat, we can do that by keeping the sample in 4K, 6K or 10K. Also we have 77 Kelvin also. And coming back to the relevant product for the conferences, we have these diode lasers, which is from Sacher, which is a tunable laser system. And then we have this nanosecond lasers, femtosecond lasers. Then we have the supercontinental lasers also, which is relevant to the topic that we are discussing today. So coming back to our main portfolio, which is scientific imaging cameras and spectroscopy system, we have different portfolios starting from spectrometers, monochromators, CCD cameras, which can be used for astronomy, which can be used for any kind of lab application, which can be used for any kind of field applications. And then you also have the microspectroscopy system. Suppose you have a microscope and you wanted to upgrade the microscope with the spectroscopy system, we can always attach the our spectrometers with a CCD camera into your existing microscope. So that is also we have. And time resolve, suppose someone is using on a nanosecond scale and wanted to suppose you are doing a leaves or some kind of plasma experiment where you wanted to excite the spectrometer in a nanosecond time scale, you can use obviously with the ICCD camera with a 2 nanosecond getting time. And this spectroscopy can be also used for Raman plasma and other kind of laser cooling, laser trapping, and quantum optics, quantum entanglement, all the applications. So this is like EMCCD cameras. That is very. I just wanted to have a 2-3 products only since we have very short time. So these EMCCD cameras can be used for many kind of materials and many kind of environment where you wanted to measure or you wanted to image under the low light applications. Suppose your light level is very low and you wanted to image your sample by exciting by with some light, you can do it that EMCCD camera. It can be used for, like as you can see in the applications, it can be used for cold atoms, ion research, quantum imaging, quantum communications also sometimes, and along with the single molecules, of course. So this is the lowest sensitivity cameras that Oxford Instruments has. So apart from the EMCCD camera, you also have this time resolves ICCD system, which has a resolutions of 2 nanosecond, and also we can do up to 5 nanosecond. So suppose we have an experiment which you wanted to excite the plasma at a very in a 2 nanosecond or 5 nanosecond getting time, then you should be using this system where we have a nanosecond time scale, where you wanted to use with a nanosecond resolutions. So apart from the of the spectroscopy, apart from the cameras, we have these cryostats for different kind of nanomaterials. Suppose we are using some materials and wanted to keep the material under the low temperature, we can do that by using the Oxford systems up to 3.4 Kelvin. We can do in a liquid nitrogen environment also of 77 Kelvin, and obviously it can go up to 300K and 500K with a high temperature upgradation. So these cryostats can be used in widely applications, for different kinds of application, where you wanted to use for the optical experiment, where you wanted to use for the electrical experiment, where you wanted to use for any kind of magnetic experiment as well. So if you have a magnet and you wanted to put the cryostat inside of the magnet, you can do that as well. We have this product called SNSPD. This is called, as you know very well, that Indian research market is going into the communication space. So more and more researchers are trying to do quantum communication research, quantum optics research, quantum entanglement research. So we have this very high efficiency SNSPD system people in RIR, Bangalore, and other places are trying to use our system. So this has a cryostat inside of the system, and then you have a different kinds of lasers. So it has this single photon detection capabilities and can be configured up to 32 channels with a low jitter and low noise. So this SNSPT system we can use whoever is working on the quantum communications or quantum entanglement. Then we have this system for Das Nano, which is a laser system for nanomaterials. It can be used for graphene, any kind of 2D materials. And you wanted to suppose you wanted to do non-contact, non-destructive experiment, or you have some graphene sample. You wanted to excite the graphene or 2D material by some terahertz source, and you wanted to capture the light from the sample into a system. Into a system means into a detector. So we have the terahertz source, we have the terahertz detector, and along with other accessories, it can be used to measure seed conductance, DC seed resistance, or mobility, and it can also obviously measure the carrier density and homogeneity. So these are the so I just go back to the slide again. So this is the system which can be used for different kinds of graphene and 2D materials, which has a terahertz source and terahertz detectors. Just wanted to just wanted to tell that why we have this laser portfolio and why we have take apart from other companies. So we have around 450 systems from Oxford Instruments in India, and we have been supporting all the systems by our engineers from different places. And as you know, the spectroscopy lasers are all interconnected subjects. So people are using our system and always go with the laser system later on. So we have the strength going ahead, and also we have this well established connection in the bioimaging market due to again the Oxford Instruments product. And also we have different kinds of connections, different kinds of systems, different kinds of installations in defense, space, atomic energy, basic science laboratories, where people are using our system for many years now, and all are repeat users. So coming back to the again the Das Nano system that I was discussing, it can be since I said it can be this non-destructive. So obviously it can be used for many applications where you don't want to disturb the samples, and it can have a resolution of 50 micron, and it can measures up to area of 20 centimeters square per minute. It can do a measurements up to 20 centimeters per square per minute of your sample. And it can use for other thin film samples as well, indium tin oxide and other materials, as you can see in my slide. So you can use for various of applications with the various of materials. So coming back to the other lasers, we have from supercontinent lasers, which can be have from it's a broadband source. Obviously, it's a supercontinent laser, so you can measure from 450 nanometer to 2300 nanometer, and it has a we have different power like a 1 watt. We have a different powers up to 3 watt. So whoever is using on a high power that can use, and whoever wanted to work on a broadband source, they can use the supercontinent lasers. And obviously we have a better reputation rates and other things. So they and also apart from the supercontinental lasers, we have these lasers from Sache laser technique from Germany. They are specialized in tunable lasers. So some researchers wanted to tune the wavelength. Suppose you are working on a 532 nanometer and you wanted to tune the wavelength for around 20 to 30 nanometer, so you can use the Sache laser system, which has a tunability, which is very low repetition rate, as well as very narrow line width of 100 kilohertz. So these systems can also be used for a variety of applications. So, uh, so this is the different kinds of lasers. We have this cryola system. We have this 213 nanometer and up to 1064. We have with the different kinds of pulse width. So you can use for different kind of applications. So basically, just to summarize, our laser portfolio has the supercontinental lasers from 450 to 2300. We have the tunable laser system for Sache lasers. Along with that, we have a material characterizations, terahertz source and detector based laser system for Das Nano. And along with that, we have a femtosecond lasers as well as picosecond and nanosecond laser as well. So just wanted to highlight that we have been participating in many conferences. Our Atos instrument stall you might be seeing in many places. And we have been supporting all the research community by helping our sponsorship or by helping our hand, because we feel that by not only with our system, we are always here to help you with different kinds of applications, with different kinds of system, and also with different kinds of measurements, with the different kinds of prospective equipment. So these are the very recently concluded conferences we have participated. From photonics conferences we have participated, and recently we have participated in the NLS conferences at IIT Kharagpur, and also on the low temperature conference at the IIT Kharagpur as well, also on the different conference on NDT and other places. So thank you very much for giving us the time for showcase our product, and thank you very much for all the people who are using our system. So we are very glad. So if you have any questions or if you wanted to ask, you can go ahead, I think. Yeah, thanks very much.
The session is open for questions.
And whoever wanted to have any other questions or any other inquiries, they can get back to us with a atosindia.com. And also my email address is trinath, trinath @atosindia.com. So whoever has any inquiries, has any questions later on, they can mail us with the details. My phone number is 9148195384. So you can always get in touch with me or my other colleague for any other inquiries.
Since there are no questions, we will wind up the session. Thank you, sir.
Thank you very much, ma'am. Thank you very much.
Now we have another technical session by Dr. Sujit Kumar Dora, Application and Sales Manager at NanoSurf India, on atomic force microscope, an essential tool for nano research. NanoSurf is a company based in Switzerland, specializing in atomic force microscopes, scanning tunneling microscopes, piece force response microscopes, etc. Dr. Sujit will be introducing research applications of atomic force microscopes in materials characterization. Over to you, sir.
Hello. All right. Thank you very much. So, hello everybody. My name is Sujit, and I work for a Switzerland-based company called NanoSurf. I am taking care of their business in India. So today, what I will do, I'll just talk a little bit about atomic force microscope. Some of you might have heard what is an atomic force microscope. Some of you may not have heard what is an atomic force microscope. So what I will do, I will give an atomic force looks like. Then what I will do, I will show what my company sells, what kind of atomic force microscopes my company sells. Next, what I will do, I will show you some applications, what atomic force microscope can do for you. And then in the last stage, I will show you what is unique to NanoSurf as a company, what products we provide, which other vendors cannot provide in market. So let's start at NanoSurf as a company. NanoSurf as a company was started in 1997 in a small garage. And I think for the past couple of years, the turnover for NanoSurf was like $2 to $3 million. Currently, we have reached approximately $60 million of AFM market. So we cover almost 20% of AFM market all over the world. We provide AFM starting from educational grade up to high-end research grade AFMs. So in India, we have an office actually in Hyderabad, where I am sitting and taking care of the application support for Indian customers. We also have a channel partner called Incarp Instruments Private Limited, and they have overall offices all over India to take care of sales and also services, installations. And for your information, we have also installed 2 months ago an atomic force microscope in Dr. Swapna Nair's lab. And we are planning to install a second AFM also in its same lab, probably in a couple of weeks' time. That is already arrived. So one of my engineers will come and start installing it as a central facility for Central University of Kerala. So we will have 2 systems here, and that's what gives us immense pleasure that we are here to provide some presentation on atomic force microscope, how things works out. So let's go ahead and talk about what atomic force microscope looks like and how you want to understand how atomic force should work. So it was the year of 1981. Before that, what happened? People had seen a lot of atoms using scanning electron microscopes, transmission electron microscopes, but all these things, whatever they have seen, they are all in ultra high vacuum. Until 1981, nobody was able to see atoms in standard ambient conditions. Just like in air, nobody had seen. So in 1981 was the year when 2 famous scientists from IBM Zurich, Dr. Winnig and Dr. Rohrer, they first showed that it is possible to see atoms in air using a special technology which is called a scanning tunneling microscope. The basic principle of scanning tunneling microscope was simple. If you have a conductive tip and a conductive sample, and if you apply a bias voltage between these two, and if you bring the tip very close to the sample, very close means I'm talking about a distance between 0.5 to 1 nanometer, then irrespective of no contact between tip and sample, there will be electron flow. Since there is no contact, still there is electron flow, we call it tunneling. So that phenomenon was taken into account by a special microscope developed by these 2 famous scientists. This is still a professor, and this professor is retired at this moment. So this process is called tunneling, and the process based on this phenomena, you got the scanning tunneling microscope. So by using this scanning tunneling microscope, for the first time, they were able to show atoms on a silicon substrates. So they were so relieved to see atoms for the first time in air that they have given a special name to these structures and they call it relief. So for the first time, they are able to show the world that it is possible to see atoms in air. And exactly after 4 years, these 2 guys got Nobel Prize for discovering this this scanning tunneling microscope. But now things have changed. So a lot of things, I don't know whether the video will run or not. Things have changed. Now it is possible that scanning tunneling microscopes can run quite fast, can show you how the single atoms can diffuse on the substrates. I don't know, this video is not running probably. But anyway, these are the single atoms, and this is a copper substrate. These are the gold atoms, and it is possible to see how these atoms jump and hop over the substrate and how much diffusion energy is required to understand the energy movement from one place to another place. So scanning tunneling microscope has reached a stage where you can take hundreds of images within seconds to show people in video rate. But there is a limitation to scanning tunneling microscope. What limitation is that? The limitation is for scanning tunneling microscope, you need extremely flat substrates. If the substrate is rough, you cannot use a scanning tunneling microscope because the sensitivity of the tip is very, very high. Second, since scanning tunneling microscope involves current, you need to have conductive samples. You cannot use a scanning tunneling microscope on substrates which are not conductive in nature. So you see there are some difficulties using a scanning tunneling microscope. So that is why people thought, if not current, what else is arc sensitive arc current? And people found out it is not only the current, it is also possible to have another factor which is called the force, that is arc sensitive arc current. So in addition to Dr. Binnick, a couple of other professors, Professor Quet from Stanford University and Christopher Gerber from University of Basel, they discovered that we can take into account force, which is arc sensitive arc current, and we can build another microscope which is based on force. And force exists practically on any kind of substance, whether it is conductive, whether it is non-conductive, whether it is insulating, it does not matter. Force exists on every kind of samples. So when your sample and your a sharp probe is far away from each other, there is practically no force acting on it. When the probe comes very close to the sample, let's say a distance between 2 to 10 nanometer, you will have forces starting to act on it, and these forces are all attractive in nature. And this is not a single force, it's a mixture of forces which includes van der Waals forces, magnetic forces, electrostatic forces. So let's say all these attractive forces act when the probe comes very close to the substrate within the range of 2 to 10 nanometer. But then tip can also touch the substrates, and when the tip touches the substrates, only force that exists, that is electronic in nature. So electrical repulsive force start to work. So until this point, when you have only no contact between the tip and tip, this is called the non-contact regime. And when the tip is completely in contact with the substrates, you have the contact regime. So standard atomic force microscopes normally works in two basic modes. It can work in the attractive regime, where you will have something called a tapping mode or intermittent contact mode, or when the tip is completely in contact with the substrate, you will have something called a contact mode. So all the advanced modes, what I am going to explain you in AFM, they are either based in tapping mode way or in contact mode way. So two basic modes are important in AFM, contact mode and tapping mode. All advanced modes related to either contact mode or tapping mode. So this is the basic principle how the things work. So let's say this is a laser, a red laser. Normally all the standard AFMs will have a red laser with a wavelength in the range of 650 nanometer up to 670 nanometer. Then the red laser falls on the back side of something called a cantilever. The cantilever looks like this. It's made up of silicon chip. This part is called the base of the cantilever. This is the cantilever, and at the end of the cantilever, there is a sharp tip. This sharp tip is not visible through naked eye. However, the entire chip as well as the cantilever is visible through your naked eye. So you can see this cantilever completely, but not this standard tip. So what happens? The laser falls on the back side of the cantilever, and then it gets reflected back and then falls back onto a detector. We call it a position sensitive detector. Whatever changes happen on the substrate, that will be detected by this detector. So what happens now? If the cantilever moves to another position on the surface, suppose there is a bump on the substrate, what happens? The cantilever has to bend. And in the same time, you saw the laser which was at the center of the detector, that also got moved. Now, the job of the AFM controller was to bring back this laser onto the center of the cantilever. So how it can do? It can move this part up. So that's exactly in AFM, happens in AFM, and then it is back. So now the movement that has happened from here to here is exactly the height of this structure. So that is how you measure the surface topography in AFM. This is called a beam deflection AFM method. And practically 99% of AFMs are all based on this method only. A laser falls on the cantilever, the bending of the cantilever in the vertical direction, provides a deflection of the laser on a position sensitive detector, and this deflection is measured in something called a volt, and that volt is converted to nanometer by something called piezoelectric coefficient, because all AFM scanners are made up of piezoelectric material, so they will have piezoelectric coefficient, which means how much nanometer per volt. So when you get this volt and you know the piezoelectric coefficient of the scanner or the piezo material, then you can calculate how much nanometer it is. But the good thing is that you are not supposed to calculate all these things by yourself. The software, the controller, all combined together will provide you the data in nanometer. So you are not supposed to do anything, provided you have calibrated your AFM completely. Your calibration of the AFM is very, very important in measurement, in AFM measurement. So AFM as a surface tool, what properties you can get out of AFM? Number one, it's the surface structure in 3D. And the surface structure in 3D does not mean only in air. AFM can work also in liquid environment, under electrochemical environment, under ultra-high vacuum, under environmental control. So this is something which can work in every medium. So you can get topography in every medium using an AFM. Additionally, on top of that, out of AFM, you can also get electrical properties, magnetic properties, mechanical properties, and also you can manipulate at the nanoscale. I will show you a little bit more how these things looks like. But let's say if you go a little bit further and get more information about the sample, what you are getting is the surface topography, which provides you the roughness, step height, structural sizes. From material contrast, you will understand what is the composition of the material qualitatively, not quantitatively. From magnetic structure, if your samples are magnetic in nature, you can perform magnetic force microscopy to get the magnetic domains. If your samples are conductive in nature, then you can measure their electrical force, you can measure their current, you can measure their work function. If your samples are piezoelectric in nature, you can measure their piezoelectricity. At the same time, if you are working on tribology, then you can measure also the friction on the sample. Similarly, for nanomechanics, by applying force onto the sample, you can measure their stiffness, their modulus, their adhesion. All these properties you can also measure. For nanolithography, you can draw something, scratch the substrate, measure the mechanical properties of a nanotube, something like that, by pushing the tip by force or by applying voltage. So this is part of nanolithography. Now, a couple of slides, I'll just show you what NanoSharp as a company sells. Then I will show you more towards application before I end my talk. So NanoSharp as a company has very compact AFMs and STMs. These are just plug and play. A couple of wires you connect it to start using either STM or AFM. These are educational grade stuff, but you can get the topographic structures, you can get atomic resolution within few minutes. Then we also have very compact AFMs which you can integrate with let's say upright optical microscope. So upright optical microscope, you can remove one of the objective and then you can integrate one of these AFM heads so that you can see large areas using objectives, optical objectives, and then you can move again with the scan head and take a high resolution image of the same area. So this is specially designed, the lens AFM is designed only to integrate with upright optical microscopes. We also have systems called nanite. If you have heard about nano indenter or ellipsometer, you will see all the time an AFM like this, because this is the only AFM available in market which can integrate with any nano indenter from any company available. Whatever company you are talking about, every company has to buy an AFM if they want to integrate with their nano indenters. So all the big companies who are selling nano indenters, they normally buy from us to combine with their systems. So this is specially designed for nano indenter and optical profilometer industry grade. Then you have research grade AFMs starting from core AFM. This is the model we have recently installed here. And we are going to install this model also in a couple of weeks' time in Central University. Then we have other models which can be integrated with inverted optical microscopes. They can also work as completely automated for measuring nanomechanical properties. And this is our recent development, which is called a drive AFM. So drive AFM is more or less fully automated. You are not going to adjust anything by using any screw or anything. You just connect the wires and you control everything via software. The laser alignment, the sample movement, the detector alignment, everything is fully automated using drive AFM. So I'm going to talk a little bit more about drive AFM. All standard AFMs follows the same principle what I told you earlier. So there is no difference um, between the principle from one AFM to another AFM. The good thing about drive AFM is that we have recently won the first prize from Willy as the best microscope in 2023. Is this drive AFM. So drive AFM has a lot of features. First feature is it can have automated laser alignment. Just clicking a couple of buttons in software, you can align the laser automatically. Number two, you can use the standard cantilevers, what is all AFM company use. You can now also use very small cantilevers to scan fast. So you can take images quite quickly within few seconds also. Then you have a controller which is the lowest noise controller available in industry. It is 28-bit controller, a high resonance scanner which can scan faster, and you have a whole bunch of accessories. And the good thing about the IDFM that it can go from atomic resolution up to 100 micron area. Any type of resolution you want to get, you can get out of it. So this is how the NanoSharp Drive AFM looks like. on top, you have the camera, and the whole part is like this. So this is your cantilever holder. Then it also comes with a new technology that a second laser falls on the cantilever, which excites the cantilever so that you can image everything quite nicely in liquid without having multiple peaks. That is called a clean drive. And more advanced version of clean drive is called web mode, which is more or less called photothermal off resonance tracking. I'm not going to explain a lot of theory behind it, but this is something where whatever you cannot get in contact mode or tapping mode, you can see those things using web mode or called photothermal off resonance tracking mode. So this system also comes with a very special software that is called Studio software, recently developed, and that software also, oops, that software also looks quite nice, quite user friendly. You can have a look how this looks like. So everything is just press of buttons and you start doing experiments. No need to touch the AFM once you have put the sample in. You just choose whatever mode you want to do, just then click buttons and start experiment. So this also comes with a special version of software called viewport, which means you can combine you can take an optical microscope image and then you can choose which area of the optical microscope image you want to do AFM imaging. So this is like that, optical microscope image overlapping with AFM image that we call viewport. This is fast scanning. If you want to do scanning fast, that also possible with the system using small cantilevers. Okay. Now let's go back to some of the applications what AFM does. Normally, if you want to see something on a micron area, you will be able to see them. Let's say some glass gratings here, which are in the micron range of 1 or 2 micron size. So you can see them easily. Same AFM scanner can go up to atomic resolution, both on material samples, let's say HOPG or graphite. This is a biological sample, so proteins, single molecular proteins also, or individual atoms on any kind of substrate you want to see. Same scanner can show you. This is something related to 2D materials. I think a lot of people have talked today regarding 2D materials. So 2D materials comes with something called Boyer pattern, which is something like an electron electron wave pattern, which is not the actual atoms, but something like a wave of the electron cloud. So that Moire pattern is very much important for people to understand how they affect the electronic properties of let's say some sort of electronic gadgets or so. So a lot of people are very interested to learn about the Moire pattern. So this is what the large structures are the Moire pattern, whereas this is the atomic scale of graphene. This is also an image you can see inside the atomic resolution. The big ones, the big hexagonal structures are the Moire pattern. If you are a biologist or you want to measure biological samples directly on a large substrate, this is some rat liver nuclei, so you can image them very well using in liquid under the real conditions. This is something you can easily get by using photothermal off resonance tracking or wave mode. Single, let's say DNA strands, you want to see them also, it is possible to see them. And you can even see how the DNA helical structures you can get the resolution by using the AFM. Same polymer, you can scan at slow speed, you can scan at fast speed, you get the same kind of resolution without any loss of clarity or resolution. Also, the web mode is very, very important to shape the quality of the tip. As you can see, scanning, this is a sample which is normally used as a standard sample to check the tip quality. So you can see the same sample is image scan 1 after scan 20. There is no change in structure. So that means the tip quality remains the same using web mode. Now, web mode is something which is very, very important to get something which is not possible to see using standard tapping mode. For example, this is the standard tapping mode. You cannot see what is inside, but the moment you perform web mode, you can easily see what is inside. So these things are not visible with standard tapping mode. So web mode, that is important. This is also another example where if you perform standard tapping mode, you will only see these large structures. You won't be able to see these all zigzag structures inside. But the moment you perform web mode, you can see all the details that is inside. Of course, mechanical properties you can measure by using an atomic force microscope, and this drive AFM can scan quite fast to produce mechanical properties quite fast. But this is not related to only drive AFM. You can use any AFM to measure mechanical properties. But of course, drive AFM produces this data quite fast. Then other kinds of applications, what is possible with an AFM, if you want to measure the current on the surface, you can perform conductive AFM. Currents can be measured from picoamps up to nanoamps level. If you are interested in measuring the work function of the sample, or you are working on solar cells or so, where you want to measure the efficiency of the solar cells, then you can perform Kelvin probe microscopy, showing what is the work function of the sample at a particular area or particular point. That is also possible to measure. These are some of the examples of Kelvin probe microscopy showing the work function. Of course, performing KPFM can be done with amplitude modulation and frequency modulation, and I'm not going to go into too details, but yes, this is the standard topography, and this is the work function or surface potential of this sample, and from here you can measure what is the work function. The work function is nothing but how much energy is required to get the outermost electron out. So that is what the work function is. If you are working on piezoelectric materials, definitely you can perform piezo response force microscopy and see how the materials are expanding and contracting by applying AC voltage. And if your samples needs high voltage, small volt, because the standard AFM can apply only plus minus 10 volt. But if you want to apply higher voltages, it is also possible to apply higher voltage to the sample up to 200 volt. And of course, PFM, advanced PFM measurements include something called dual actuation resonance tracking, where if your samples are susceptible to high voltage, you can perform something called a contact resonance PFM, where signal gets amplified even at low voltages. But anyway, that is something called dual actuation resonance frequency. In addition to do PFM expansion and contraction, you can also do lithography by applying voltage to the sample, demonstrating how the materials expands and contracts, and how much expands and contracts. You can also get the quantitative data, what is how much nanometer it has expanded or contracted. You get the D33 values or D33 values out of these samples by measuring the spectroscopic data. If your samples are magnetic in nature, then you can also perform the magnetic measurements on your sample using a magnetic cantilever. And of course, not only measuring the magnetic domains, it is also possible to apply external magnetic field to the samples and demonstrate how the magnetic fields are changing by applying external magnetic field. That is also part of experiment, applying both in plane and out of plane magnetic field. If you want to do some sort of manipulation, let's say here somebody has demonstrated how much force is required to cut a graphene layer, demonstrating the stiffness of the graphene layer. So this is one of the measurements in one of the US universities. But anyway, so doing lithography, such kind of lithography is also possible, that you are applying force or apply voltage, and then you scratch and you measure what is the force required to cut something, what is the stiffness of the material. That is also part. This is something called scanning microwave microscopy. If you are into semiconductor research, then instead of applying, because the standard cantilever vibrates only in kilohertz or in megahertz frequency, it is also possible to use special types of cantilevers which can vibrate in gigahertz frequency, up to 5 to 6 gigahertz frequency. And since their bandwidth is so large, their sensitivity is also very high. So using scanning microwave microscopy, you can demonstrate the capacitance quantitatively, and you also provide the dopant profile like N-type, P-type materials. So you can study all these things via scanning microwave microscopy. This is a special addition to atomic force microscope, where instead of using the standard cantilevers, what you can use some cantilevers which can be vibrated in the megahertz range using some vector network analyzers. And there are some special cantilevers available from some special companies. So if you want to measure dopant density, capacitance, all these things are possible to measure. Then in the last step, I will only show you what is unique to NanoSharp at this moment. Whatever I showed you, all these points, this is more or less related to very much all kinds of AFM companies. This is not related special to NanoSharp, but this is our data, so that's why I demonstrated you. But now what is unique to NanoSharp and no other company can provide you is this. One is called customization, and the second one is called a fluid probe microscopy. So what customization we can do? First customization we can do if you have very large samples. Let's say you have 200 millimeter, 300 millimeter sample, even 1 meter sample. Let's say you have 1 meter sample and you don't have time to measure one by one the entire area. It is possible to make a fully automated system which measures thousands or which takes thousands of images automatically for quality control. So recently we have provided up to 7 million AFM instruments to companies like Zeiss Microscopy, who wants to perform on large wafers fully automated roughness measurements. They take thousands of images for whole weeks. So fully automated AFMs for measuring very large areas, even as I told you, even for samples up to 1 meter, 2 meter, that is also part of our customization, which we can do. If you have some samples which are concave or convex, the standard AFM cannot measure. Standard AFMs always move parallel to the substrate. It cannot move like this. So we have designed special stages which can move like this, keeping the AFM scan head all the time parallel, even to the concave or convex. So this is also part of customization, which is not normally available in market. You have to come back to us if you have a particular sample or a particular problem where you want to have something. Similarly, for optical industries, people have bought this kind of AFMs where they want to image or scan on all angles of the prism, because they cannot use a standard AFM to do all these kinds of measurements. So we have also designed something like this for optical industries, where they can measure whatever roughness they want to measure on all angles with all automation and everything. And then the last part, which is special to NanoSurf, is fluid probe microscopy. In this part, instead of the standard cantilevers, what you are using to do all kinds of measurements I showed you, it is now possible to make holes inside cantilever, and that those holes looks like this. The holes can be at the end of the cantilever, sharp cantilever. Hole can be at the side of the cantilever. Hole can be only on the cantilever without the tip. So this setup looks like this. This is the hollow cantilever, which is connected to a reservoir, and the reservoir is connected to a pressure controller. So this whole part can be connected to the AFM scanner to perform something called fluid probe microscopy. So this is nothing but a multifunctional nano manipulation tool. I will show you few examples how they look like, but it has a lot more applications. So the applications look like this. If you want to study cell adhesion or mechanical properties, you want to inject something at a particular area of the substrate, you want to do some lithography, non-destructive lithography, you want to isolate some materials, or you extract something, or you want to do some nanolithography. All these types of experiments are possible. I'm going to show you a couple of examples only here. So let's say this is an electrochemical deposition process. So you keep your sample at the potential where material normally gets deposited. Then you put the liquid through this cantilever hole and then drop it wherever you want, and then it will get deposited, producing structures as per your choice. For example, some people have made some vertical nanowires in SEM. They look like this. So they have, wherever they want, they can make vertical nanowires by manipulating on the substrate. Of course, this method is also used for in semiconductor industries to find some defective areas where they can put some material and fill it up at a nanoscale. But this is one example that local electrochemical deposition can produce vertical nanowires. Another one is if you want to make some structural structures on the substrates, or you want to put some organic molecules at a particular area, by increasing the deposition time, you can produce some spots on the substrate, which is called spotting. Then if you want to do lithography in liquid through the cantilever, you can drop liquid onto the substrates and make nice nanowires. And once it is done, you can always take a picture, and by controlling the process, you can have nanowires of different widths, different sizes. So those things also it is possible to do using an AFM. So this is more or less an overview of what you can do using AFMs and what is unique to NanoSurf. And I have not explained all the details of individual modes, which are more theoretical, or you need more information how to do these experiments. But this is an this is an overview of what an AFM is capable of. If you need more information on a particular mode, or you have a particular problem that you don't understand how to image the sample, or what properties you are getting you don't understand, you are welcome to come back to us. We have the address here. This is my address. This is my colleague's Dr. Prakash address, and this is my mobile number. So, and Dr. Nair and his students are already using AFM, so they are more or less used to the system now. They are doing all those experiments. So they are already becoming, I would say, more or less close to expertise level. Probably in a couple of months, they will also start explaining you all these things if you want more information. But yeah, you are always welcome to come back to us anytime if you have any information, or if you need any information or any application regarding atomic force microscope, and we are there to provide you the solution, whether it is a customized solutions or a standard solution, or you have a special thing what you want to understand, then you are always welcome to come back to us. Thank you very much.
Thank you, sir. The session is now open for questions.
Hi, it was a nice presentation. Actually, we have discussed during the first installation. I was there, I think.
Yes.
Even, yeah. So regarding biosample, you see, usually cells will be submerged in the liquid actually
Yes.
when we do in the plate actually.
Yes.
Can we use directly in that state, to see the topology of the cell?
Yeah. AFM is actually a surface technology, surface characterization
Mhm,
tool.
mhm.
So whatever you want to image, that has to be attached on some sort of substrate. If it is floating in liquid, it is not possible to image.
No,
that.
it won't be floating. Cell will be attached. Above that, some kind of liquid will be there, because
That is
otherwise cell
practically
will
fine, sir.
dry.
Fine.
Cell will dry.
That is exactly what do people when some people want to do imaging of cells or bacteria in live condition. They always use buffer solutions similar to one which is required for the live condition of that cell or so. So once the cell or your biological sample is attached to the substrate, after that you can use any kind of whatever
Liquid.
buffer you want to use for your substrate, you can use them. So that is called imaging in liquid under live conditions. That is practically possible.
Yeah,
Yes.
live condition.
But only thing you need to remember that the concentration of your buffer solution should not be high, because if it is too high, then there will be a lot of salts floating in liquid, and those salts will produce disturbances in AFM scanning. It will produce noise in image. So you need to find what is the lowest concentration of your buffer solution that is possible to use to keep your sample live. Except that, there is no other requirement. You dip the cantilever in, approach, once it is reached on the substrate, you start scanning. Of course, for biological samples, biological samples are extremely delicate. So you cannot use contact mode imaging for biological samples. You have to use tapping mode imaging.
Okay.
But now I already showed you that it is also possible. There is a special mode available called clean drive, which also will show you a single peak in liquid also. And that peak, you just choose that peak, approach, and start imaging like in air. No difference, no problem at all. But yes, biological imaging needs low force, softer cantilevers. Normally for biological imaging, people use cantilevers which has force constants in the range of 0.1 Newton per meter up to 1 Newton per meter. You cannot use cantilevers something like 30-40 Newton per meter. That's too stiff for biological samples. But yeah, softer cantilevers, low force, tapping mode, and low concentration of buffer solution, that is required for sample imaging in biological samples. And sample has to be attachable. So that are the 4 conditions.
Another question is, see, sometimes we fix the cells. I don't know whether you come across that kind of example where we will fix for normal fluorescent microscopy when we do, or confocal when we do. We fix the cells with the paraformaldehyde, and it will be totally dehydrated sample. Will be on the substrate. So that also we can use it, right?
So when you are using
fixed
let's say
cell.
paraformaldehyde or so, normally most of the time it is for me the samples will die because it is not.
Yes.
It
The
will
cell
die.
will die.
It will
Cell
die.
will die.
So it is not live.
It is not live. I mean, dead cell.
That is still easier.
Easier, right?
That is still easier than live imaging. Because live imaging samples are more delicate than once the sample is dead, it is already stiff. So you will have no problem imaging them.
So actually, why I'm asking is, when I'm infecting the cells with the viruses, and then live imaging a little risky, because some viruses, as you know, it is infective. So if I fix the cells and then see the surface topology of the cell membrane and all, that's what I was thinking. Maybe fixed cell also, probably we can check it, right? So the one what you're going to install here in physics department, we can actually use this sample also, right?
Sure. So the idea is, if you want to keep it live, then you cannot use paraformaldehyde.
No, then it will die actually. But also infective mode also is little difficult. I mean, virus, I work with virus, so that's And another question, the integration of this system with the inverted microscope, optical normal microscope.
If you want, you can, the one that is coming, that will be compatible with inverted microscope.
The one you're going to install newly, right?
That is supposed to come now. That is possible to combine with inverted microscope. But the one you already have, that is also have possibility to combine with something called digitally inverted optical microscope, where you can use only single objective at a time.
Okay.
So you can use single objective, take optical image. That is called demo. So demo
okay.
option is possible with core AFM, the system that is already have.
Okay.
The system that is coming, that is perfectly integrable with any
Okay.
optical microscopes, including Leica, Nikon, Zeiss,
Okay.
Olympus, whatever systems you have. But there are a couple of more accessories required for that, like an adapter is required.
Adapter.
Because the stage is different for AFM and stage is different for the optical microscope. That adapter we supply.
Okay.
And also the optical microscope condenser should have a working distance, let's say around 73 millimeter or higher. If the
Okay.
working distance is lower than that, the scan, there will be no distance to put the scan head in between.
Okay. Okay.
But yeah,
Okay.
that is two requirement. The object, let's say the adapter and the condenser should have working distance somewhere around 73 millimeter or higher.
Okay.
Except that any optical microscope that is available in market, all fine.
Okay. Thank you. Thank you very much.
Any more questions?
Yeah, I have a short question.
Yes, sir.
I think very nice demonstration and wonderful speech you gave on this applications. Actually, my question is, in actual fact, what is the resolution that you can offer on any machine? I'm talking about realistic resolution.
Yeah. Yeah.
When you talk about 7 nanometer, 10 nanometer, 3 nanometer, then maybe you report 1 nanometer. I don't know. What is the actual realistic? You are going to your record.
Yes.
Tell me what's the actual
Yeah.
resolution that
So-
you can get.
So there are actually two different types of resolution we are talking about. One is the theoretical resolution of AFM, and one is the actual resolution of the image. The theoretical resolution of AFM is very simple to calculate. You have the scanner range, you have the scanner which has a 100 micron range, and then you divided that with the controller bit. Let's say you have a controller which is 28 bit. So 100 micron divided by 2 to the power 28, you will get a value which is called the theoretical resolution limit of AFM. Normally that comes in picometer. But an AFM is nothing related to the bit resolution. It is related to the radius of the cantilever probe, which is scanning the substrates. If your cantilever is sharp enough, you can go up to atomic resolution. For example, I showed you already HOPG or graphite, which has a lattice constant somewhere between 0.34 nanometer or so, that you can see if your tip is good enough. You cannot see it every time on if your tip is 10 nanometer or 20 nanometer radius, you won't be able to say that. But it is fully dependent on the tip radius. But the capability of the AFM is there that you can go up to atomic resolution.
Let's say we have a brand new tip
Yeah.
that you gave us, and what is the resolution of the feature that we can measure? That's a question.
Yeah.
I mean,
Let's say all standard cantilevers, what you are using, they have a radius between 5 to 10 nanometers. So I would say 2 to 3 nanometers you can get. But beyond that, if you want to make sure that you want to go 1 nanometer resolution X and Y, I would suggest that you can use super resolution cantilevers like single carbon nanotubes grown on cantilevers, which can go beyond 1 nanometer.
no, the one that you have already supplied to us, and also the one that is forthcoming.
But the cantilevers you have to buy. The one you have now, they have a resolution around 5 nanometer at this moment.
I'm not sure that we are getting that kind of resolution.
Probably you have not either, but we have demonstrated that to someone called Professor Mandar Deshmukh, TIFR Mumbai, because he wanted to see this Moire pattern. The Moire pattern I showed you.
I know Mandar Deshmukh. I know, but then what is the difference then that in TIFR, is it something to do with the vibration isolation, the preparation?
No,
or is that
it's the
anything
same thing. It's all about, I would say, this is, sometimes you will see, you cannot guarantee because the cantilevers are always made by electrochemical etching process. And this electrochemical etching process, controlling them at nanometer level is practically impossible. So which cantilever will show you that resolution, you cannot guarantee. Some cantilever, there is capability of AFM, but is also dependent on the cantilever. So the idea is, as I told you, the cantilevers, there are many cantilevers in the market. So if you try one cantilever is not working, you can also try another cantilever. But the capability of AFM is always there.
Because we also have to want to measure some magnetic domains, MFM mode, and want to resolve some
Yeah,
magnetic domains of the size of a few nanometer.
The good question you asked about a good question about magnetic domains. Yeah, magnetic domains are different because the cantilever you are using for measuring magnetic domains, they are coated with a magnetic material already.
I just wanted to digress a little bit. In both cases, measuring surface morphology as well as magnetic domains, what we are looking for is just to measure on the nanometer scale, a few nanometer scale.
Okay.
Is this possible?
Yeah, as I told you, if you want to see magnetic domains beyond 10 nanometer, it won't be possible because the problem is the magnetic cantilevers are coated with certain magnetic materials, which makes the diameter of the magnetic cantilevers almost 20 nanometer. The standard cantilevers have a radius between 5 to 10 nanometer. At the same time, the moment you coat it with magnetic material, the radius becomes like 20 nanometer or so. So for that matter, the lowest resolution you can go with a magnetic cantilever somewhere between 10 to 14, 15 nanometer. So below that, it won't be able to show you anything. You cannot see it.
Hello, sir.
Hello.
Already we have discussed about the things, but I would like to know some more discussion because we are working in the PVDF nanofibers. So you already showed some figures based on PVDF TRFV. So I would like to know how we can perform because I'm facing the difficulty to do PFM in this type of nanofiber mats. So they are saying that there is already always attractive force between this PVDF fiber and the tip is got broken. So how we can do this PFM, that is local piece of force response I need. So
Yeah. When you are measuring the PFM signal, normally what happens for standard AFM, what you are doing, this is your cantilever, you are putting the laser at the end, right? And then you are taking the topography. So the problem when you are doing electrical measurements, there are not only PFM signals, but there are also electrostatic forces that is acting. So what you need to do, you don't need to put your cantilever laser at the end of the cantilever, but you need to put the laser slightly behind. So in that way, whenever the electrostatic force happens, it will not affect your PFM measurements because the first force that will attract the sample is the electrostatic force if your sample is conductive in nature. And you need to get rid of that. To get rid of that, your force has to be higher than electrostatic force. So in that case, if you put your cantilever laser at the end of the cantilever, it will not show you the actual PFM signal. What it will show you the electrostatic curve, which you think probably looks like a butterfly claw, but that is not the actual PFM butterfly. That is actually the electrostatic butterfly. So you don't need that. So normally when you want to perform your PFM measurements, you need to have a very good contact between tip and sample. So for that matter, if you move your laser from end to slightly inside, so this means this position has to touch the substrate because the detector will think that the laser is here. So this part has to touch the substrate. So this means it will always apply higher force to the substrate. And that higher force you need because that higher force is higher than the electrostatic force. So once the force is high on the substrate, after that, if the sample is up and down by applying voltage, it will not be any more electrostatic. It will be only PFM signal that you are supposed to see, right? So all the time try PFM signal or PFM measurements by bringing the laser slightly inside, not at the end. End never gives you the right PFM signal. Second important part when you are measuring fibers is that you have to see how your fibers behave at what voltage. It's easier to do lithography first, and then you can perform spectroscopy. Let's say you have taken a sample large area, 5 micron area at let's say 2 volt or 0 volt. Then you take a 3 micron area by applying a positive 5 volt. Take 1 micron area, apply negative 5 volt, and make the voltage 0 again, and take the entire image. One part when we are applying negative voltage, that will be aligned in an opposite direction compared to the positive voltage, right? So that's how you see the lithography. So if you see the lithography structure on your substrate, you are sure that it is supposed to show the spectroscopic data also. If you are not seeing any lithographic data, that means the voltage what you are applying to your sample is not enough to provide you spectroscopic data. So in that case, either your sample needs higher voltage, but there are also other constraints using PFM signal. Let's say some samples do not like high voltage. If you apply high voltage, sample breaks down. So in that way, as I already, probably I gave you already some information, there is something called dual actuation resonant frequency method. In that method, instead, all these PFM signals what we are performing are away from the resonance. You are performing signals in the range of 10 to 20 to 30 kilohertz, whereas your resonant peak is around 150, 160 kilohertz. So far away from resonant frequency, you are imaging, right? So this is all called off resonance PFM measurements, what you are doing at this moment. Now, if you choose the frequency not at 15 or 17 kilohertz, but at the contact resonance, your frequency will get amplified. Sorry, your signal will get amplified. But the problem is, the moment you do at contact resonance, not only your signal, but also the topographic signals will combine with the PFM signal. So for that matter, it is also possible that you can use a second lock-in amplifier from outside to separate the PFM signals out of topographic signal, so that you can see PFM signal and topographic signal side by side. That is called dual actuation resonant frequency imaging. But for that matter, additional accessories are required, and it is only applicable if your samples are susceptible to high voltage. If your samples are not susceptible to high voltage, you do not need DRT mode. You can perform everything off resonance mode, applying higher voltage either to the tip or to the sample. Both cases are possible.
Okay. Is there any limit for thickness? Actually, we are preparing 70 micrometer nanofiber mats. So somebody is telling that it's not possible because thickness is high. So is there any limit for thickness? Actually, I already did samples in thin films and nanotubes that I could measure
But
very perfectly.
nanotubes are already too small, right? They
Yeah,
cannot be
that
that
already.
thick, right?
But it has some length of micrometer and 100 nanometer diameter. Okay, it's already I got, but in this fiber samples, the thickness is 75 micrometer because it is a matte
Okay.
and randomly aligned fibers.
Mhm.
So, is there any difficulty for doing this type of samples?
That as I told you, you can try as a high voltage PFM measurements if it is not an, because if it is too thick, maybe the voltage, the AFM by itself can apply voltage up to plus minus 10 volt, not beyond that. But if you want to apply voltage beyond 10 volt, you need some external high voltage amplifier. You can apply voltage to the sample or to the tip individually, where you can apply, let's say 150, 200 volt to the sample or to the tip. So you can try to apply high voltage if it is not possible to use the standard voltage and not showing any lithography. But as I told you, before doing spectroscopy, you try lithography. Apply positive voltage, negative voltage, zero voltage. See if you are seeing some lithographic structures. If you are seeing lithographic structures, that means it is expanding and contracting.
Okay.
So beyond that, you don't need to think about whether it is electrostatic or not, because if it is showing lithographic structure, that means that is PFM signal. And if that voltage is enough to perform or to show PFM lithography, that voltage should be enough to show you spectroscopy. If not, then not. You have to apply higher voltage. And if your sample is susceptible to high voltage, then you can think of dual actuation. If not, then high voltage should be enough. 200 volt is already a huge amount voltage. Applying on a particular area of few tens of nanometers, so that's already huge amount of energy. So that should work for almost any kind of sample if it is possible for that sample. If not, then either dual actuation or it will never work.
Okay, sir. Okay. Yep. Thank you.
Yeah. All right. So any further questions?
Thank you, sir, for the detailed explanation. It was quite informative.
Thank you very much. Thank you very much all. Thank you very much.
I request Dr. Rajendra Pilangata to give away a memento.
How is that? Yes, sir. Thank you, sir. Thank you very much. Yeah. Welcome. Tomorrow I'm available. You can talk further, sir.
Thank you, sir.
Yeah.
Participants, please note that the parallel session 2 short invited talks has been come to an end. Parallel session 3 oral presentations O20, O23 to 26 is currently progressing in Narmada building. Participants, please note, parallel session 2 O23 to O26 is currently progressing in Narmada building.
This marks an end of the first day of the International Conference on Functional Materials for Advanced Technologies 1. We hope this day sparked up your mind with knowledge, ideas, curiosities, and questions. We urge you to look forward to the coming days too. Also, we will have cultural programs here at the same venue at sharp 6:45 p.m. Enjoy the evening. Thank you.
Hello. Hello. Cut.
Please make sure to be back here at the same venue by 6:45 p.m. to witness cultural programs. Thank you.
അടുത്തത് അനുഗ്രഹീത കലാകാരൻ രഞ്ജിത്ത് അവതരിപ്പിക്കുന്ന ഡബ്ബ ഓണാക്കിട്ടാ പറയുന്നത്.